Okay, hopefully you already got some of this done, but I'm going to start with intercepts. Actually, no, I'm not. What do you notice about this one when you start working on it? What jumps out at you? Anybody? Anything? Mm-hmm. How do you know that? Yeah. And when I look at this as a division question, like fraction is like a division question, right? I can do the division. I can do this divided by this because it's 1 degree smaller, so I can actually do that division. And that's kind of the way I think about it in my head. If they were flipped, you couldn't divide, or you wouldn't divide, right? And so that's a different kind of question. Something we've talked a lot about is like how you do this part, I guess, in your head, like how you actually figure it out, and then also knowing the difference between the test for a vertical asymptote and the test for a horizontal asymptote and the test for an oblique asymptote. Like that's something you really want to have a good grasp of. So I'll put in a number just to the left of -3, like -3.1. And I think I'm going to use this. So the bottom is going to be negative because it's -3.1 plus 3. And this is negative and this is negative. So 3 negatives. So this is trending to negative infinity. And then when I put in like -2.9, I get 2 negatives on top, but the bottom is positive. So this one looks like it to me one positive. For the oblique asymptote, we have to do the division. So however you want to do it. For the oblique asymptote, we talked about why f at x equals this, but you don't have to show that every time, in case anybody was wondering. But you do want to make this statement, and then this is what I like to do. So then the oblique asymptote is y equals 2x minus 3. You got to know which part is the asymptote and which part is the remainder, which I like to call r at x. Okay, so that's what I have done so far. So we want to test around the oblique asymptote. There's lots of different ways that we've talked about showing this. Just make sure that it's clear. You can use kind of any of the ways that we've done in class, but don't make up something entirely different. This one's easy. When I put a negative 100, it's just negative on the bottom right, so it's less than 0. So it's below. And above. Next, critical values. I'm just rewriting the function so I have it here. Try to take the derivative and simplify it. All right, this is what I have so far. How's that? So here's where I want to stop and think about this for a second together. When we first started curve sketching, at this point we did our first derivative table, or critical values table, to determine, and again, like, it all makes sense at the time when you're doing it, but then all of a sudden you've got all these different skills and they do all these different things, they tell us all these different things, and if you haven't really worked through it, you might get to this point and be like, wait a minute, what does the first derivative even tell me? Like, what does it even, what do I get from it? What am I doing with it? So think about that table. What are we testing for in that table? What does it tell us? What does the first derivative tell us about the function? How many people think they know? Couple, maybe, yeah. Emma, what do you think? Yeah. Good. If there's a turning point, anybody want to add to that? See, what were you thinking? Okay, good. What else? In general, how would you answer that question? What does the first derivative tell us? Slope of the tangent? So the sine of the slope of the tangent related to like turning points, but is it increasing or decreasing, right? Like that's the end result of that table, is we're breaking it up into the intervals where it's increasing and the intervals where it's decreasing. And then using where the derivative is equal to 0 and where it does not exist to come up with those important points. And we can sketch with that. But we're going to do a second derivative table as well, so we don't have to do first derivatives table now. But it's important to know that that's what it tells me. But I do want to get some information out of this. So even though I'm not going to do the first derivatives table, what do I want to get? Well, I do want to get where f prime at x does not exist at x equals negative 3. I always want to state that, even though it's really irrelevant because it's a vertical asymptote. It's not always a vertical asymptote, just FYI. Doesn't always work out that way, so be mindful of that. And what else do we want to figure out? Emma said where the top is 0. Does anybody want to tell me anything about this? Yeah. How do you know it doesn't factor? Nice. So b squared, which is 12 squared, which is 100. What just happened here? Which is 144 minus 4 times 2 times 11. I always say this is useful to do because if you end up doing the quadratic formula, we want that number 56 anyway, right? So that doesn't mean we don't do it. It was positive, not a perfect square, so it's not factorable, but it's solvable. So f prime at x equals 0 at x equals negative b plus or minus the square root of, there's that b squared minus 4ac, which works at 56, over 2a and we don't have to show a lot of work here. We're trying to streamline this process. I don't even have to show that second step for sure with the 56 in it, but it might make it easier to plug into your calculator. And I believe those are the two values that we get. And you could do it here, you might do it later, but we eventually want to know, this is negative, this is supposed to be negative as well, they're both negative. Negative 1.129 and negative 1.5, negative 4.871 and negative 16.5, approximately. Okay, we want those 2 points. That's the point of the sketch, is we're labeling the important points, so we want the whole point. Not doing the table, but we still want to figure out where the first derivative is 0 and where it does not exist. Everybody okay? Any questions so far? All right, next. Second derivative. Same thing, I'm going to let you, well, I'm going to write down all of the stuff just so I have it at the top of this page, but let's see. 2x squared plus 3x minus 2 over x plus 3. All right, give that one a try. Okay, hopefully you got this part done. Here's the first line. And this is where it gets a little bit tricky, and maybe the easiest way is to factor. Like I would common factor the top, the x plus 3 out. And then after, maybe you just expand and simplify. But I do notice that I can factor this. And if I factor that, I'm just going to factor a 2 out so I can common factor that 2 out. But I don't know. Like it's a little bit more taxing on your working memory and just your brain in general if you're trying to do too much at once. So don't overdo it. I don't think it ends up being a lot of value, but I'm going to try it anyway. So I can factor out a 2 and an x plus 3. So I factored 2 out of that first bracket. So that first bracket is now 2x plus 6 times x plus 3 minus, and I've factored out all of that, so I'm just left with that. Oh my gosh, don't forget to distribute that negative. You don't have to do it here, obviously, because we got one more step, but don't let that be the mistake that you make. All right, so I'm going to let you try to take over from there. Maybe a bit of a surprising answer. I don't know. Again, I can see that if you did a question like this for the first time on a quiz or a test, you've never seen one, you might be like, ooh, that I don't think it's supposed to work out that way. Are you allowed to get just a number on top? And of course, you can get anything, so nothing wrong with that. What does that mean? I don't know that we need to think about what it means, but does anybody have any ideas about what that means? We get just a number, just 14 on top. What does the second derivative tell us? Nice. Very nice. No points of inflection because it's never 0. So it tells us about concavity. Remember our lesson last week, the title was concavity. Is it concave up, concave down? So it doesn't mean the concavity doesn't change because we do have an asymptote, but it means that there are no points of inflection. Whether you knew that or not, when you start building the table, you'd probably determine that when you start trying to draw the graph, it's going to come out and we're going to see that. So you don't have to necessarily think about that now. F double prime does not exist at x equals -3. Again, that's a vertical asymptote, so it's no big deal. And F double prime, here's what I can say. I should make a statement on it. Does not equal 0 for all x. Okay, let's do our table. So it's just going to be x less than -3 at -3 and x greater than -3. That's it. We still do our table with checking concavity around the asymptote. Super easy because all I have to do is put in some big negative number. This is another mistake that people make though. What number should I pick for the first one? Somebody want to give me a number to use? What should I pick? Jason, what do you want me to use? Negative 100. Negative 100 plus 3 is negative 97. Negative 97 cubed is, I don't know, but negative, right? So when you square a negative, you lose the sign, but not when you cube it. Be careful of that. Some people going too fast and don't think about it and forget that odd exponents behave very differently from even exponents. So this is still negative. So here it's negative. Here it does not exist. It's a vertical asymptote. And then x bigger than negative 3, I could use 0 or I could use 100. And I get positive. So this is concave down. And this is concave up. All right, let's draw our graph. Ooh, I got lots of space here. That's good. So I need to think about my intercepts. I need to think about, and before you start doing this, you probably want to look at all of them. You might even relist it if the information's on a couple of different pages, so that you can space things out properly. So let's see, we've got intercepts at 1/2 and negative 2, vertical asymptote at negative 3. My oblique asymptote is 2x minus 3. So those are all pretty reasonable. And critical values at negative 1.1 and negative 4.8, 4.9. So lots of stuff to the left. Okay, so negative 2. Sometimes I even use like if I'm doing this on paper, I often use my ruler and just roughly measure out where 1 is, where 2 is, where 3 is, maybe mark it lightly or something like that, just so that it's somewhat to scale, but it's not super important. It's negative 2, 1/2, those are intercepts. Negative 3 is an asymptote. Again, if I was doing this on paper, I'd be using a ruler for this. The oblique asymptote, something we've talked about a lot. You got to be able to draw a straight line. So I go down 3, and then the slope of positive 2. So it's doing something like, in fact, I'm going to try to use a ruler. Something like this. Y equals 2x minus 3. There's that asymptote. Oh, shoot. Yeah, no, I don't want that there. This is a part that's hard. Not labeling the line. That's not what I'm talking about. Sometimes these oblique questions, part of the sketch is like way far down. Okay, can we start drawing it? So here's another thing I want to think about. I have a turning point at negative 1.1 and negative 1.5. So it's like around here somewhere. And then behavior around asymptotes, as I approach the asymptote from the right, it's going up to positive infinity. And when I approach the oblique asymptote, goes out to positive, goes out to the positives, we approach from above. So that's pretty plain, pretty straightforward, nothing interesting happening there. And then here's that other part though. I'm going to mark this point. Negative 1.13, negative 1.5 is that turning point. And the other turning point is negative 4.87, so it's to the left of negative 3 here somewhere, and negative 16.5, so it's like way down here. That's what I was saying, is sometimes it goes way off. And it approaches the oblique asymptote from below and goes to negative infinity when it approaches the vertical asymptote from the left. So there you go. In the end, a very straightforward curve. My y-intercept is really hard to get in there, but negative 2/3. There we go. Any questions? Are you sure? We're going to do one more. We only have 20 minutes, but we're going to do it anyway. What I'd really like is if we can get to the end of this one, and then I want you to try to draw it without my help at all, and then we'll just compare our graphs. And again, I would encourage you as much as you can, do all of this work on your own. Maybe you can't help doing this, but if I were you, like every step of the way, I would think to myself, how easy or how obvious is it to me what the y-intercept is, what the x-intercept is? And if there's anything that's not obvious, then really think about that. Like go back and look at how we find it. Don't just sit there and copy it from me. Everybody should be able to come up quickly with these intercepts. And if you can't, just be aware of that, and then let's talk about it, or go back and look at some old examples to come up with the pattern so you really see it yourself. The intercepts are 0 and 0, which if your y-intercept is 0, your x-intercept's got to be 0 as well. You might have other x-intercepts, but right, that's hopefully an easy one. Once you find a y-intercept of 0, you know you got an x-intercept of 0. And I'm going to look at this one here and put a big negative numbers, big positive numbers. Sorry, no, it's not what I'm doing at all. I'm putting in numbers close to 1, which are going to be positive. So everything, the bottom's always going to be positive, and taking the cube of a positive is always positive. So these are all both going to be positive. Again, that's something that the faster you're at, the more you understand it, the better you are at doing that. Whoa. Better off you're going to be. You're not going to lose time. These sketches are long enough that if it also takes you a long time to really get those behaviors. I don't know. Does it mean you need more practice, so you need to talk to somebody about it, or you need to think about the sketch, or that kind of thing? I don't know. What do I have to do for the oblique asymptote? This is important. If you've never done a question quite like this, you might get stuck here. Yeah. So I've got, we didn't talk about how it's oblique, but it's degree 3 on top and degree 2 on the bottom. And some people might try to use synthetic division with that, but that's not going to work because it's squared. So we have to use long division here, right? So it's going to be x squared minus 2x plus 1. And what do I have to do to the other part? I need all these ghost terms. So x cubed plus 0x squared plus 0x plus 0. Because it was just x cubed on top. Kind of strange. And we did this a little bit at MHF, but not very often did it work out like that. But this is the thing, is often when we're doing curve sketches, we get these wonky things happening. Very quickly, if you're trying to do long division, you're trying to figure out what this is. It's like, how many times does x squared go into 2x? The number you're putting here is the number or the thing that I want to multiply this by that will turn it into that. So x squared times 2 gives me 2x squared. That way, when I subtract, I'll get 0. That's the whole point. So that's my trick, is like, what do I multiply this by, right? Okay, so we got our oblique asymptote and our remainder portion. Again, do our test. Negative 100, the bottom is going to be positive, and the top is going to be negative, so this is less than 0. And this is going to be greater than 0. Good. There we go. So I've got f prime equals 0 at 0 and 3. And at 0, that's an intercept. I already know that. So that's one of my points is 0, 0. Something's going on there. And the other one is 3. And I plug that into the original function. I get 3 cubed on top, so 27. And 9 minus 5, which is 4. So it's 27 over 4, which I'll need later. Kind of trucking through this one because, like I said, I want you to have a chance to really sketch it and compare your sketch to mine before we go on. Everybody okay with that? All right. Points of inflection. Equals x squared times x minus 3. X minus 1 all cubed. I'd say for this, we want this expanded. If you didn't expand it, you'd have to do the product rule on top and then the quotient rule as part of the quotient rule, and that would be pretty messy, so I think it's a lot easier to expand it. Derivative of the top times the bottom. Again, I see that there's some stuff that I can common factor to maybe simplify this, but the order in which you do this is entirely up to you. That's why you got to kind of figure it out for yourself. But I'm going to factor 3x out of that first bracket. So 3x and x minus 1 all squared. And when I factor out a 3x, I get x minus 2 times x minus 1. So the 3 is gone, the x minus 1 squared is gone, and there's an x factored out of there. All right, let's see what happens here. 3x, I get x squared minus x squared is gone. Negative 3x plus 3x is gone, so times 2. So this is 6x over x minus 1 to the 4th. Whew. Oops. Something's going on at 0, 0. It popped up in every single one of those things, eh? So there's something serious going on there. So we're going to build our table and then do our sketch. So it's 0 and 1, so x less than 0, 0, between 0 and 1, at 1, greater than 1. So we got concave down, we've got concave up, and concave up. So for the change from concave down to concave up means we have a point of inflection. And it's at 0, 0. We've already established that. And that's vertical asymptote. I think we have everything. What do you think? Any questions? All right, go ahead and hopefully, if you're a little bit behind, you get caught up quickly. And we've got about 5 minutes. Let's see if we can sketch this. Good morning. Yeah. Too, for some people might be there's so much information, where do I even start? And I mean, we've seen this before obviously, but just pick something, start putting in your intercepts. I see a lot of people drawing in their asymptotes, and maybe that's the easy part, is the intercepts and asymptotes, and then where do you go from there? Start putting together the behavior around asymptotes, that sort of thing. Make sure you've graphed your oblique asymptote correctly. Think about concavity. It's concave down before the x-intercept, and concave up after. There's my asymptotes. Okay, so concave down is like this, and it's approaching the asymptote from below over here. So it's going to be like that. And then concave up afterwards, and it's approaching the vertical asymptote from the left is going up to infinity. So that's a point of inflection, right? So it comes in and goes, has that twist right at 0, 0. And the derivative is equal to 0 there, right? It's a horizontal tangent line. That's what happens when you have that twist. And then this one's just simple, and I'll mark this point. It was 3 and 27 over 4. And that's it. Any questions? So that one was a little bit different.